Hi everyone. Yeah, this is Dr. S. Venkateswarlu, working as a professor of EC at IARE, Hyderabad. Yeah, today we are discussing about design of finite impulse response filter. FIR as a class of linear time invariant filters. So for this, we require that we know that all digital filters with one is IAR, second one is FIR. Under this FIR, we try to design that finite impulse response filters. We try to analyze that FIR as a class of linear time invariant filters. For this, we have to analyze that all transfer function of the filter is followed by what we call h of z, where where h of z is equal to, so y of z, we know that y of z by x of z. Okay, here. So where y of z by x of z is equal to the summation k equal to 0 to m bk into z power minus k by 1 plus the summation k equal to 1 to n ak into z power minus k. Here find it with reference to the transfer function of the filter. So we have to design of the FIR filter. We have to analyze that FIR as a class of linear LTI filters. So for this case, finite impulse response FIR filters where capital N is equal to 0. Here it is, the 10 value. Here we are right to substitute that where N is equal to 0. Okay, where if it is N is equal to 0, no feedback. Okay, this is the major agenda while we are designing to that FIR filter. The FIR filter, finite impulse response filters. Here it is with reference to this h of z. This h of z is equal to y of z by x of z is equal to the summation k equal to 0 to capital M into bk into z power minus k. Okay, by 1 plus the summation, here it is the summation where k equal to 1 to capital N. Okay, this capital N should be here, it is 0. Okay, so well, that means where N is equal to 0, no feedback. Okay, let us consider an FIR filter of a length m, order n is equal to m minus 1. What should that order number of delays? So with this, the output response will be ready to observe in mathematically, where y of n is equal to the summation k equal to 0 to m minus 1 bk into x of n minus k is equal to the summation k equal to 0 to m minus 1 h of k into x of n minus k. So with this, where x of n is ready to analyze this mathematically using this all block diagram, unit delay with reference to v unit delay, x of n is fed to this unit delay. So we have to verify that v of n. So mathematically, we are having this mathematical analysis graphically we have to represent here. For FIR filter of the length m, order n is equal to m minus 1. Watch out this order number of delays. Okay, with this can immediately obtain the impulse response with the x of n, with the x of n, what do you call, where x of n is equal to where x of n is equal to delta of n. Okay, so with this can immediately obtain the impulse response with x of n is equal to delta of n. Try to verify that where h of n, where h of n is equal to y of n is also equal to summation k equal to 0 to m minus 1 became delta of n minus k equal to bn. Okay, this is can immediately obtain impulse response. Mathematically we have to verify here. The impulse response is of the finite length m as required. So note that FIR filter, finite impulse response filters, have only zeros, no poles. Okay, hence known also as all zero filters. So FIR filters are also known as feed forward, or we can consider non-recursive. Okay, or we can consider transversal concept. These are all major significance while you are designing that FIR filter. FIR, where finite impulse response filters, also known as a feed forward or maybe non-recursive or transversal. Okay, so with this, the impulse response is finite length m as required. FIR, finite impulse response, have only zeros, no poles. Hence, that FIR filter is known as all zero poles, or we can consider this condition. FIR filter have only zeros, no poles. Okay, with this, distal finite impulse response filter cannot be derived from analog filters. Rational analog filters cannot have a finite impulse response. Why both? Because of they are inherently stable. That's one aspect. Second one is they can be designed to have a linear phase. And third one, there is a great flexibility in shaping their magnitude response. We require always that magnitude response, the good, there is a great flexibility in the shaping their magnitude response. Okay, so like fourth one, they are easy and convenient to implement. Okay, remember very fast implementation using FFT. Okay, how it is fast, we know that. Here, after that, we have to decide that distal finite impulse response filters cannot be derived from analog filters. Rational analog filters cannot have a finite impulse response. So, with this, the FIR filter, the finite impulse response filter, where output response is y of n is equal to the summation k equal to, where the summation k equal to 0 to m minus 1, h of k, x of n minus 1, x of n minus k, since h of n, x of n are the finite duration sequences. Where which one here? That h of n, and where x of n from that equation, so are the finite duration sequence. These two are the finite duration sequence. Finite duration sequences. So their convolution is also finite in duration. So the duration of the sequence y of n is, that where duration of the sequence y of n is equal to L plus m minus 1. Okay, so go on using this all values, L and m value, try to analyze that all y of n. That y of n is maybe, since we have to analyze the h of n and the x of n are the finite duration sequences, their convolution is also finite in duration. The duration of the sequence y of n is L plus m minus 1. Yeah, let us consider that n, okay, that n greater than or equal to capital L plus m minus 1. Already we know that the duration of the sequence FIR filter y of n, for the duration of sequence, reference to that equation, y of n is L plus capital L plus m minus 1. If we are using consider normally in initial cases, let us consider n capital N greater than or equal to L plus m minus 1. Let us pad the sequence h of n and x of n with 0 to increase their length to capital N and perform the endpoint DFT. So this is the background of what you call endpoint DFT. Because of capital N greater than or equal to L plus M minus 1, okay, the sequence h of n and x of n with the zeros to increase their length to n out of the filter and perform the n point DFT. The frequency domain equivalence is where we have to verify that y of k. So y of k, where y of k is equal to h of k into x of k. Okay, where here where y of k is equal to, what is that, uh, h of k and x of k. Okay, so here it is that y of k is equal to h of k into x of k. So where here with k is ready to substitute this k value. Okay, the k value, we know that k value. Normally that k value is equal to, what is that? So 2 pi k, but here it is n by k, or it is what you call capital N, where sometimes where k it is also equal to that 2 pi k by capital N. Like this, we will try to analyze the frequency domain. Equivalent is y of k is equal to h of k into x of k. Okay, now that endpoint DFT, you know that all in the performance, the perform the endpoint DFT. Okay, that is followed by y of k, and then endpoint I inverse of discrete Fourier transform y of n can be used for compute the standard convolution product and this to perform. Okay, like this. Let analyze next FIR filter design methods. Basically, we know that this is the standard method impulse response truncation. The simplest design method has undesirable frequency domain characteristics, not very useful, but it introduced to, so in the normal general purpose cases, we require that impulse response truncation. The simplest design method has undesirable frequency domain characteristics will appear, not very useful for, but it is somewhat in normal cases. It is very much used, that impulse response truncation. The next one, windowing. So one is impulse response truncation. Next, windowing design method. Windowing design method. It is simple and convenient, but not optimal. This is the second popular method while we are designing the FIR, finite impulse response design methodologies. So the impulse response truncation, the second one may be windowing. This is also popular method, windowing design method, simple and convenient but not optimal. That is order achieved, not minimum possible. Okay, optimum filter design methods. Okay, next third one is optimal filter design methods. So back to our ideal low pass filter example, we have to analyze for designing this FIR filter design methodologies based on this all popular method. So we will try to design this using this all methodologies. We require certain stuff background. So for this case, back to our ideal low pass filter example. So let us consider, for example, a simple ideal low pass filter defined by what you call SD of omega is equal to 1 if mod omega less than or equal to omega c. 0 if omega c less than mod omega less than pi. It can be shown easily that the impulse response is given by what you call SD of n is equal to what you call omega c by pi sine omega c n by omega c n. Okay, so desired impulse response has a sine shape. okay, which is non-causal and infinite in duration. For this case, here by using this all, what is your observation? What you call clearly cannot be implemented in practice. This is the sometimes the merit, sometimes the demerit. Okay, with this, the what you call low pass filter, ideal low pass filter backgrounds. Okay, this Hg of omega, analyzed, it can be shown easily that the impulse response is given by Hg of n is equal to omega c by pi sin omega c n by omega c n. Okay, so where h of n, here it is h of n infinite in duration. To compute any sample of the output, we need to know all samples of the input, both in the past and the future. Here it is unacceptable. So what if we just clip off the sign at some large n? Okay, approximately h of n is equal to sine of n into omega c by pi n, or mod n less than or equal to m and 0 otherwise. Like this, we write analyze that all to compute any sample of the output. We need to know all samples of the input, both these past and the futures. Here is that the frequency response now looks like for omega c equal to typical values, that is substitute 0.4 pi and what you call different values of m. Okay, so if it is, we know that all condition where for what you call that n value, for n mod n less than or equal to capital M and zeros normally. But here if it is different values of m value, if it is different m values, so go on varying that all these m values. Okay, where if we are ready to initialize that all, where omega c is equal to typically 0.1 pi or 0.2 pi, or maybe sometimes I to use that 0.3 pi for frequency response looks like for these values response will be varies, and 0.4 pi and different values of m. So one observes that ripple in both pass band and stop band, and transition not abrupt. Like here it is what you call leading to the transition band. Like this, we write analyze using that for designing our FIR filter with the ideal cases, or maybe if it is background of this all, if they are using the different what do you call h of n, infinite in duration and unacceptable sometimes. So if we just clip off the sign at some large n value, if it is here also that n value is ready to go on increase that, where initially 0 to maximum value 0, 1, 2, 3 and so on. Okay, so next approximated filters obtained by the truncation. Here it is the transition band gets the narrower, where m tends to infinity, the ripple remaining. Here it is, if it is initially that n where m is equal to 15, so the transition band is right to observe when h of e power j omega versus normalized frequency. Okay, so the transition band is right to observe here. If it is gone increasing the m value where m is equal to 30, okay, so here what is the normalized frequency from 0 to 1, and h and e power j omega 0 to what you call 1.2. Okay, next if it is gone increasing that one, which one, the transition band gets narrowed as m up to infinity, but here is where m is equal to 200, so it will vary that normalized frequency versus h and e power j omega and so on, where m is equal to what you call where m is ready to substitute 1000. So like this, the transition band gets narrowed as m tends to infinity. The ripple remains. So approximated filter obtained by the truncation. Okay, now coming to these are all related to the truncation methodology. Now coming to the next methodology is window design method. Okay, while we are using this window design method, to be expected, truncation is just pre-multiplication by the rectangular window. Normally, we know that rectangular window, Kaiser window, Dahl-Chebyshev window, um, yeah, a lot of popular windows are available. Here, the rectangular window, initially they are using that using the rectangular window. We will expect that window in design methodology with the help of rectangular window. The truncation is just pre-multiplication by the rectangular window, where it is followed by where that omega n is equal to what you call 1 if n is equal to 0, 1, 2, 3 and so on, m minus 1, 0. Otherwise, this is not very clever or obvious one introduced with a delay. If we go on using this value n where n is equal to more than that m or m minus 1. So here the Fourier transform h of omega of the truncated filter h of n is equal to hd of n. Omega n is what you call where h of omega is equal to 1 by 2 pi, okay, integral minus pi to plus pi hd of lambda into w omega minus lambda into d lambda. So where h of omega is the Fourier transform of the rectangular window. Because of the truncation is just pre-multiplied by the rectangular window. With reference to this, the Fourier transform of the rectangular window is followed by w of omega is equal to e power minus j omega of capital M minus 1 by 2 sine of omega m by 2 by sine of omega by 2. Okay, so coming to the next one, utilizing this rectangular window frequency response. How we are responding this using this all omega n is if if the n is equal to 0, 1, 2, 3 up to m minus 1 values. So what is the spectrum convolution? Where rectangular window, the Fourier transform of the rectangular window. So we are analyze here it is rectangular window frequency response. For this, for Fourier transform of the rectangular window, you know that one. So where w of omega is equal to e power minus j, what do you call w of omega is equal to e power minus j omega of m minus 1 by 2 into what you call sine of omega capital M by 2 by sine of omega 2 admits as a magnitude and phase response. With this, w of omega is equal to sine of omega m by 2, okay, by sine of omega by 2. Here it is omega less than or equal to pi. Okay, where theta of omega, we know that when sine omega m by 2 greater than or equal to 0. How it is analyze this one, where omega of m minus 1 by 2 plus pi, that is where w of omega has piecewise linear phase. We will observe this all piecewise linear phase. While we are using the rectangular window frequency response, we will observe that all where w of omega has a piecewise linear phase. Okay, so practically one uses the truncated and delayed impulse response. Approximately h of n is equal to h of approximation n minus m minus by 2, where h of n approximation is equal to omega c by what you call that omega c of sine sine omega c n, okay, where it is omega c by n pi, okay, sine of omega c by n by omega c n, okay. Here it is, you have to initialize that m minus 1 by 2, m minus 1 by 2 are into, and where m is, where capital M is the filter length, and n, and where n is equal to, the out of the filter, is equal to what you call m is the filter length. Filter length minus 1. Filter length minus 1 is known as filter order, or order of the filter. Okay, with this, what is the year after using this all practical? One use the truncated and delayed impulse response. User can analyze this one, that the order of the filter is ready to calculate. Order of the filter ready to calculate, that n is equal to capital N is equal to capital M minus 1. If it is m is equal to 10, okay, how we are calculating the 10 value, where order of the filter is equal to 10 minus 1. It means order of the filter is what we call 9 only. Like this, you write analyze that order of the filter or filter order. Okay, with this delaying operation, introduced the linear phase term. The resulting filter is casual and has a linear phase. Okay, with this, magnitude of the rectangular window frequency response is ready to observe here graphically, where if it is width of the main lobe is this one, and peak of the side lobes are ready to verify, and width of the main lobe, if it is main lobe, side lobes are increases, and main lobes are it is varies and increases. Rectangular window where m is equal to 16. That means where n is equal to m minus 1, here m is equal to 16 minus 1, where n is equal to 15, or what you call like this, right? Analyze this, or how we are practically magnitude of rectangular window frequency response is with this width of the main lobe is typically ready to verify, and the peak side lobes when compared to width of the main lobe. Okay, this is the graphical representation of magnitude of rectangular window frequency response. Now ready to observe the truncated filter, where using this all ST of e power j omega and W of e power j omega is ready to observe. There is here the higher the area under side lobes, the larger the ripple in the passband and stop band. Like this, the truncation filter ready to analyze with this graphically. Okay, so if it is the width of the transition region between the passband and stop band in h of omega increases, okay, with the width of the main lobe of w of omega. Okay, like this, right, to analyze. Next, ideal requirements for designing this our digital filter FIR. We have to follow these ideal requirements. Ideally, we would like to have capital M small, few computations, W of omega close to a delta direct mass for the H of omega to be closer to SD of omega. Okay, where SD of omega is equal to, here we know that where SD of omega is equal to what do you call, here it is 1 if mod omega less than or equal to omega c, okay, 0, okay, 0 if here it is 0 if whatever you call omega c less than or equal to mod omega less than or equal to pi. This is our ideal low pass filter. Okay, if it is high pass filter and high pass, low band pass, band stop, and so on, it will varies that all the right to utilize the ideal. These are the ideal requirements for designing our FIR filter. So these two requirements are conflicted if you are using this one, or that how we are avoiding this one. So here it is increasing the dimensions of the window. So normally that m value initially that where m is equal to 0 to up to what you call 1000, already we have seen that one, how it is truncated and so on. For that, with reference to that, if m is equal to 10 or m is equal to what you call 30 or maybe 20 or maybe 35, where m is equal to 45 and 50. So best one is that 50, where m is equal to 60, 70 and 80. So here you will observe that where m is equal to, here that m is equal to 10, where m is equal to 30, where m is equal to 50, where m is equal to 80, where with normalized frequency versus normalized amplitude. If it is m is equal to 80, so that you are at verify the graphically. How many side lobes or main lobes are there? It is displayed. If it is m is equal to 30, the number of side lobes are increasing, main lobe is reduces. If m is equal to 50, number of side lobes are increasing, the main lobe is reduces. So if it is going increasing m value, if m is equal to 80, so side lobes are increases here. Okay, main lobe is reduces. Okay, the width of the main lobe decreases as m is increases. Okay, the area under side lobes remaining constant as m increases. This is increasing the dimensions of the windows. You try to verify that all performance levels for designing your what you call finite impulse response digital filter. Okay, conflict the ideal requirement. The width of the transition region between the passband and stopband in the h of omega increases with the width of the main lobe of W of omega. The ripple in the passband and stopband is dependent on the area under the side lobes. For the rectangular window, the width of the main lobe decreases as m increases. Okay, but it can be shown that the area under the side lobes remain constant. Okay, transition region gets smaller, but the ripple remains. The problem: sharp discontinuity of the rectangular windows. Using this all analysis, finally there is a problem with this while you are using this all under this conflict ideal requirement. If it is h of omega increases and the width of the main lobe of what do you call it, W of omega, the ripple is the passband and stopband is dependent on the area under the side lobes. For this rectangular window, the width of the main lobe decreases as m increases, we have seen, but it can be shown that the area under the side lobes remain constant. Okay, the transition region gets smaller, but the ripple remains. Okay, the problem is sharp discontinuity of the rectangular windows. Thus, we go for okay by using this all observing this type of problem, go for the further windowing technique. So for this problem, what is the solution? So solutions to sharp discontinuities of the rectangular window. Okay, here use the windows with no abrupt discontinuities in their time domain response, and consequently two side lobes are in their frequency response. So on using this all analysis, directly we to avoid that particular problem, sharp discontinuities of a particular window like a rectangular window. In this case, the reduced ripple comes at the expense of the wider transition region, but this, however, so this can be compensated for by increasing the length of the filter. So alternative windows time domain. Many alternatives have been proposed. Best example: Hamming, and Blackman. here the sample versus what you call windowing windows, that m is equal to more than that 10 or 16. So it is where is that all alternative windows for the time domain. Okay, with this window magnitude of frequency response, the frequency response is what you call, right, to verify that with this Fourier transform window is m is equal to 16 or below, also how it is varies the Hanning and the Blockman. Practically it is possible by writing the piece of code in MATLAB. So right to verify that the magnitude of the frequency response, so that to write to analyze that all FIR digital filter designs. Okay, summary of this window characteristics. So these are the windows name, rectangular window. The main lobe is right up there 4 pi by m, and main lobe side lobes are minus 13 decibels. Peak 20 log base 10 delta is minus 21 decibels in the rectangular window. A Hanning window 8 pi by m, and the main lobe or side lobes minus 32 decibel, and peak what do you call peak 20 log base 10 delta equal to what do you call minus 44 decibels. If you are entering that Hamming, it's same value here, it is the main lobe, but here it is main lobe and side lobes are somewhat is increases. That here it is the peak value is minus 53 decibels. Coming to the Blackman, 12 pi by m, here it is somewhat is increasing, and the main lobe is minus 58 decibel, and the peak that is minus 74 decibel. So with this, after that, you can choose that all window with reference to window characteristics of that, right, to design our FIR filter. Okay, so with this we see that clearly that window transition region, wider main lobe is compensated by much lower side lobes and thus less ripples. Okay, so for with the windowing techniques, easily right to analyze what do you call it, different aspect that our FIR filter will ready to design, to reach that are our design aspects. So using this rectangular window, right, to see we're ready to verify different windows other than this rectangular window. One may be a Hamming and Blackman window, how it is varies. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.